Currently, a sophisticated observation device, positioned 1 million miles from Earth, is gazing into the distant past. The findings it consistently uncovers are unexpected and perplexing. The James Webb Space Telescope was initially conceived to validate our existing understanding of the cosmos. Instead, it is fundamentally challenging it. It is revealing galaxies of immense size, stars that coalesced with unprecedented speed, and a universe that appears to disregard its own established principles. We are about to embark on a journey through discoveries that have left physicists astonished. We will explore the numerical discrepancies that defy calculation and the profound questions that remain unanswered. What if our perceived reality of the universe is not the true one? If you find this exploration engaging, please consider liking and subscribing. It significantly aids our reach. Take a moment to prepare. We are commencing our journey now. On the 12th day of July 2022, the National Aeronautics and Space Administration unveiled a groundbreaking image. This photograph represented the most profound infrared depiction of the universe ever captured. Within it, thousands of celestial bodies, known as galaxies, were illuminated against a celestial canvas roughly equivalent in size to a single grain of sand held at arm's length. Scientists had eagerly anticipated this moment for many years. The James Webb Space Telescope, a project costing $10 billion, required 3 decades to bring to fruition. Its purpose was to observe so far back in time that researchers anticipated encountering nascent, unformed, and disordered galaxies just beginning to coalesce and stabilize. However, what they actually observed caused several scientists to pause mid-statement during the official announcement. The galaxies featured in that initial image were not haphazardly formed. They were not young or struggling to materialize. A considerable number of them were colossal, meticulously structured, and brilliantly luminous. They resembled galaxies that had undergone billions of years of development, yet the light-reaching Webb originated from those galaxies when the universe was merely a few 100 million years old. This presented a temporal paradox. There simply hadn't been sufficient time. This contradicted everything previously understood. One astronomer, upon reviewing the collected data the subsequent morning, described the sensation as opening a door expecting a small chamber and instead discovering an entire continent on the other side. The prevailing cosmological model, the established scientific framework detailing the universe's origin and evolution, had generated precise predictions regarding the early cosmic landscape. It forecasted a diffuse atmosphere of hydrogen and helium gradually cooling in the aftermath of the Big Bang. The model anticipated the emergence of small structures, a slow and steady growth process, and gravity gradually aggregating gas clouds over hundreds of millions of years, culminating in the faint illumination of the first stars. Webb, however, revealed something entirely different. It detected objects of such immense mass, brilliance, and structural completeness that some researchers began to unofficially label them as impossible galaxies. This designation was not due to a violation of logical principles, but rather because, within the context of our current cosmic evolution model, there was no conceivable physical mechanism that could have facilitated their formation at such an accelerated pace. Consider this analogy. Imagine observing a time-lapse video of a skyscraper under construction. You understand the established sequence, foundation first, followed by the structural framework, then the individual floors, and finally the exterior glazing. This entire process typically spans 2 years. Now, envision initiating the playback and, within the initial 30 seconds, witnessing the 50th floor already completed. The lobby boasts marble flooring, and people are actively dining inside. In such a scenario, you wouldn't declare the building to be impossible. Instead, you would logically conclude that there is an error in the recording or the playback mechanism. This is precisely the situation Webb presented to the scientific community during the summer of 2022. It delivered a recording that did not align with the expected construction schedule. In the ensuing months, the data continued to pour in. More galaxies, more intricate structures, and more objects in locations where they were not anticipated to exist. Research papers began to surface, initially tentative, then progressively more assertive. Phrases such as "challenges current models" started appearing in their summaries. A few publications went further, suggesting that these findings require fundamental revision of galaxy formation theory. The scientific community, rather than succumbing to panic, engaged in rigorous recalculation and meticulous verification of the instruments. Webb's instruments underwent thorough scrutiny. The data underwent repeated analysis, and consistently, the results remained the same. Something fundamental in our comprehension of the universe is inaccurate. The crucial question is the extent of this inaccuracy, and the answer is still being actively formulated in real time by the very individuals whose professional lives were dedicated to the model that Webb may have just disrupted. However, the impossible galaxies were merely the initial revelations from Webb's observations. What followed proved to be even more extraordinary. Prior to Webb's transformative impact, scientists possessed a well-established narrative. This narrative, meticulously constructed over decades and rigorously tested with numerous telescopes by thousands of researchers, was known as the Lambda Cold Dark Matter model. For an extended period, it effectively accounted for virtually all observed cosmic phenomena. The narrative unfolds as follows. Approximately 13.8 billion years ago, the universe originated from an infinitesimally small, incredibly hot, and dense singularity. Within the first second of its existence, space itself underwent expansion at a rate exceeding the speed of light. Within minutes, the initial atomic nuclei were formed. For the subsequent 380,000 years, the universe existed as a radiant, opaque plasma, too hot and dense for light to traverse. Subsequently, it cooled, the plasma dissipated, and light flowed freely for the very first time. This ancient light, now faint and stretched by billions of years of cosmic expansion, is something we can still detect today. Scientists refer to it as the cosmic microwave background radiation. Following this transition, gravity assumed dominance. Minute fluctuations in density, barely perceptible, initiated the clumping of matter. Hydrogen clouds began to aggregate. These aggregations then became more dense. Subsequently, the first stars ignited, possibly around 200 million years after the Big Bang. Initially small and dim, more stars progressively formed. These stars then coalesced into the earliest rudimentary galaxies. Over billions of years, these galaxies merged and evolved, transforming into the massive, structured spiral and elliptical formations we observe in the present day. This represents established scientific understanding. The temporal sequence is robust. The mathematical calculations are consistent. Observations from earlier telescopes supported this framework for decades. The critical descriptor in this timeline is slowly. Galaxy formation was posited to be a protracted, arduous, and multi-generational process. It involved billions of years of growth, collisions, and mergers. Nothing was thought to be capable of accelerating this process, as nothing can surpass the speed of cause and effect. Webb was intended to serve as the ultimate validation of this model. By examining the universe at an age of merely a few 100 million years, Webb was expected to confirm the early stages of this prolonged, gradual process. It was predicted to reveal faint proto-galaxies, chaotic gas clouds, and the raw, unrefined material that would eventually shape the universe we observe today. Instead, Webb peered into the past and found the complete structures already in place. It discovered galaxies possessing more mass than our own Milky Way, already fully formed, already organized, and in some instances, already in a state of decline, existing in an epoch where they should have been barely beginning their existence. It is important to emphasize that these are not theoretical conjectures, but confirmed detections. The light emanating from these objects is verifiably real. Their distances have been ascertained through multiple independent measurement techniques. What remains unknown, and this is a crucial point, is the underlying reason for their existence. The detection is irrefutable. The explanation remains an enigma. Consequently, scientists are now faced with a critical decision. Either a component of our galaxy formation model is erroneous, necessitating a substantial revision of established textbooks, or our understanding of the early universe is fundamentally flawed, a realization that carries even greater implications. Both possibilities have been under consideration since 2022, and neither has yielded a clear-cut resolution thus far. However, there is one particular galaxy that Webb identified which propelled the discussion from theoretical speculation to urgent inquiry. This singular object compelled researchers to scrutinize their screens and vocalize the question, how is this even conceivable? Its designation is lengthy and technical. Consequently, researchers refer to it by a shortened identifier, GS 9209. What Webb definitively confirmed about this galaxy in 2023 sent a significant shockwave through the astronomical community, a rare occurrence in recent scientific history. This galaxy is, in astronomical terms, dead. This is not a metaphorical statement. In astronomy, a dead galaxy is one that has ceased forming new stars. The essential gas required for star birth has been either depleted or expelled. The galaxy now relies solely on the light emitted by its existing stars, gradually diminishing over billions of years. Dead galaxies are a common phenomenon. We observe them extensively throughout the nearby universe. The perplexing aspect, however, is the timing of its demise. Based on the light captured by Webb, this galaxy generated the vast majority of its stars within a remarkably short window of approximately 800 million years. Furthermore, it accomplished this entire process within the first 1.8 billion years following the Big Bang. By the time the universe had reached less than 2 billion years of age, this galaxy had already completed its entire productive lifespan and fallen silent. Consider the profound implications of this. Our own Milky Way continues to form stars even today, approximately 13 billion years after its inception. This ancient galaxy, however, completed all its stellar formation, amassed hundreds of billions of stars, then ceased all activity, all before most other galaxies had even properly commenced their development. To grasp the magnitude of this, envision a scenario where an individual is born, matures, raises a family, establishes a successful career, retires, and passes away of old age, all before their neighbors have finished constructing their very first house. This is the scenario Webb has revealed. What elevates this discovery beyond a mere anomaly and confirms it as a significant observation is that Webb has since identified multiple galaxies in comparable states, massive, mature, and fully developed, existing in an era when such maturity was theoretically impossible. This is not an isolated, aberrant data point. It represents a discernible pattern. The prevailing scientific hypothesis suggests that an external factor must have triggered a rapid phase of star formation within these galaxies, subsequently followed by an equally swift cessation. A leading theory implicates supermassive black holes situated at their centers. When a black hole actively consumes matter, it releases immense quantities of energy. This energy can expel gas from a galaxy, effectively cutting off the fuel supply necessary for new star formation. This phenomenon is known as quenching. The existence and occurrence of quenching in galaxies are confirmed. What remains uncertain is whether this process can transpire rapidly and early enough to account for Webb's findings. The mathematical calculations are challenging to reconcile within current theoretical frameworks. Another potential explanation, still in its theoretical stages, posits that our understanding of the rate at which dark matter halos form in the early universe may be inaccurate. Dark matter halos are essentially the invisible structural frameworks that surround galaxies. If these halos formed at a faster pace than our models predict, then the galaxies within them might have also developed more rapidly. Webb is not definitively disproving our existing models. Rather, it is uncovering subtle inconsistencies. Each galaxy exhibiting these characteristics represents an additional fissure in our current understanding, and within these fissures lies a much older enigma, one that scientists were aware of even before Webb's launch, and one that Webb has made considerably more difficult to disregard. There exists a universal clock that governs all cosmic processes. It does not tick in the conventional sense. Instead, it expands. When astronomers state that the universe is 13.8 billion years old, this is not an arbitrary estimate. This figure is derived from several independent methodologies, each cross-validating the others. These include the rate of cosmic expansion, the temperature of the cosmic microwave background radiation, and the age of the most ancient observable stars. These diverse lines of evidence converge with remarkable precision on a singular answer. Therefore, the overall age of the universe is not in dispute. The universe is approximately 13.8 billion years old. This fact is well established. What is currently under scrutiny is the magnitude of events that can transpire within this temporal framework. Galaxy formation adheres to specific principles. Gravity, while potent, is not an instantaneous force. Gas clouds require a finite duration to collapse. Stars need time to ignite and initiate nuclear fusion, producing heavier elements. These elements must then be recycled through stellar demise before subsequent generations of stars can emerge. Galaxies must undergo mergers and accretion to grow. None of these processes occur instantaneously, nor can they be accelerated beyond certain fundamental physical limitations. The models developed by physicists over decades were predicated on these inherent constraints. They calculated the rate at which the universe could generate structures of varying sizes and masses, operating under the established laws of physics. These calculations aligned perfectly with all observations made with previous generations of telescopes. Then, Webb extended its gaze further into the past, and the established timeline began to falter. In 2023, a team of researchers published an analysis of 6 galaxies imaged by Webb. All 6 originated from the very early stages of the universe, within the first 700 million years after the Big Bang. Critically, all 6 possessed greater mass than our current models would permit for objects of that age. One particular galaxy was so far outside the expected parameters that its lead researcher conveyed to the press that it was causing him sleepless nights. This language transcends routine scientific discourse. It reflects a researcher confronting an outcome that defies established expectations. The issue of mass becomes more significant when aggregated across Webb's numerous observations. It is not confined to 1 or 2 galaxies. Across multiple observational surveys, Webb consistently detects more mass present in the early universe than our models predict should exist. The total observed stellar mass at high redshift, indicating very early cosmic history, appears to be approximately 10 times greater than that produced by our most sophisticated simulations. Tenfold. This discrepancy is not indicative of a minor calibration error. It points to a fundamental structural problem with the model itself. To be precise, this remains an area of active scientific debate. Some researchers contend that the disparity might diminish as measurement techniques evolve. Others maintain that it signifies a genuine deficiency in our understanding of how cosmic structures emerge in the early universe. Both viewpoints are championed by respected scientists employing substantial datasets. The consensus among all involved parties is that Webb has exerted considerable pressure on the cosmic timeline, a level of scrutiny that previous telescopes could not achieve, and the timeline is not the sole element under strain. There is another figure, even more fundamental, that has been the subject of contention within physics for over a decade. Webb has amplified these arguments considerably. This concerns the rate at which the universe is expanding and the persistent disagreement between two groups of scientists regarding its precise value. In 1929, Edwin Hubble made a discovery of paramount importance in the annals of scientific history. He ascertained that galaxies are receding from us, all of them, in every direction. Furthermore, the greater the distance to a galaxy, the faster it appears to be moving away. This provided the initial concrete evidence that the universe is in a state of expansion. Galaxies are not traversing space independently. Rather, space itself is stretching, carrying these galaxies along with it, analogous to dots on an inflating balloon moving apart from one another. To quantify the rate of cosmic expansion, scientists employ a value known as the Hubble constant. This constant indicates the speed at which a galaxy recedes for each unit of distance separating it from us. Accurately determining this value is one of the most crucial endeavors in all of cosmology, as it establishes the fundamental scale for numerous cosmic parameters, including the age of the universe, its observable size, and, ultimately, its eventual fate. For decades, two primary methodologies have been utilized to ascertain this constant, and for decades, they have yielded divergent results. The first method involves examining the early universe. Scientists analyze the cosmic microwave background radiation and employ our most advanced physical models to calculate the expected expansion rate in the present epoch. This yields one specific numerical value. The second method focuses on the local universe. Scientists utilize particular types of stellar explosions, known as Type Ia supernovae, as cosmic distance indicators. By measuring the distances to these celestial explosions and the velocities of their host galaxies, they directly calculate the expansion rate. This approach produces a distinct numerical value. The disparity between these two measurements is termed the Hubble tension, and it is a well-established phenomenon. It has been corroborated by multiple independent research teams employing numerous distinct techniques. Both measurement approaches have undergone exhaustive verification. The discrepancy between the two values is approximately 9%. In everyday contexts, 9% might seem insignificant. However, within the realm of fundamental physics, it represents a critical crisis. The reason for this is as follows. If both measurements are indeed accurate, and the evidence strongly suggests they are, then either our model of the early universe is flawed, or our comprehension of the universe's evolution from its initial state to its present condition is incomplete. There is no alternative explanation that can preserve the integrity of both. Webb was anticipated to play a role in resolving this tension. It provided new, more precise measurements of those supernovae that serve as distance markers. The results, published in 2024, were not reassuring. Webb's measurements corroborated the existing discrepancy. The Hubble tension did not dissipate. In fact, the enhanced precision made it more challenging to attribute the issue to measurement errors. Consequently, the universe, according to two rigorous and extensively validated measurement methodologies, is expanding at two different rates simultaneously. This statement may sound paradoxical, but it is the conclusion supported by the available data. Some theoretical physicists propose that this indicates the existence of missing physics. This might involve a brief surge of energy in the early universe, termed early dark energy, which temporarily altered the expansion rate and left an enduring imprint on the observed mismatch. Others suggest that the solution lies in an even more unconventional direction, as there may be an additional, unseen component within the universe, something invisible that constitutes over a quarter of all existing matter and energy. And Webb's observations are beginning to imply that our understanding of this component may also be inaccurate. Dark matter cannot be directly observed. No telescope ever constructed has detected its emitted light, as it produces none. It also fails to reflect light. It interacts with ordinary matter almost without resistance. For all practical purposes, it is invisible, yet we are overwhelmingly confident in its existence. The evidence supporting its presence stems from gravitational effects. Galaxies exhibit rotational patterns that cannot be accounted for by their visible mass alone. If a galaxy contained only the stars and gas that we can detect, its outer regions would rotate too slowly to remain gravitationally bound. They would eventually disperse over time. Instead, they rotate at speeds comparable to those of the inner regions, implying the presence of a massive, invisible entity providing gravitational anchorage. This entity is dark matter. This is not a speculative or fringe concept. Dark matter is one of the most rigorously tested and well-supported inferences in modern astrophysics. The evidence for its existence is derived from galactic rotation curves, gravitational lensing phenomena, the large-scale structure of the cosmic web, and the cosmic microwave background radiation. Every investigative avenue leads to the same conclusion. Approximately 27% of the universe's total energy content is comprised of dark matter. Within our standard cosmological model, dark matter plays a crucial role in galaxy formation. It coalesces into invisible halos, vast spherical regions of gravitational influence, which act as the initial seeds around which ordinary matter aggregates. Gas is drawn into these halos, cools, and eventually forms stars. The dark matter halo serves as the foundational structure, and the galaxy is what is subsequently constructed within it. The model predicts how these halos evolve over time. They begin small, merge with others, and progressively increase in size. The larger the halo, the more massive the galaxy it can ultimately support. This developmental process, like all aspects of the standard cosmic narrative, requires a considerable amount of time. Webb is discovering galaxies in the early universe that are so massive that the dark matter halos capable of hosting them should not have yet formed. The necessary scaffolding should not be in place. Construction should not have commenced. Consider it in this manner. You intend to construct a skyscraper, but to do so, you first require a foundation. And to pour the foundation, the ground must be prepared. This preparation process necessitates a specific duration using the available machinery. If someone presents you with a fully erected skyscraper situated on ground that was only cleared yesterday, you would not question the skyscraper itself. You would question the timeline of the ground preparation. This is the fundamental challenge concerning dark matter that Webb is bringing to light. One potential explanation, still theoretical, suggests that dark matter halos in the early universe formed more efficiently than our current simulations indicate. It is possible that the conditions immediately following the Big Bang permitted more rapid aggregation. If this is the case, our simulations require recalibration. Another possibility, more radical and still subject to debate, is that dark matter behaved differently in the very early universe compared to its present state. Some researchers have proposed that dark matter may have possessed distinct properties at high temperatures, which would consequently alter its aggregation rate. A third option, considered unsettling and still representing a minority viewpoint, is that dark matter is fundamentally different from our current understanding. This last possibility would necessitate not merely an adjustment to an existing model, but a complete reconstruction of it. And there is one specific piece of data from Webb that persistently draws researchers back toward this uncomfortable third door. This data pertains not to the appearance of galaxies, but to their spatial distribution across the sky. The pattern they form is one that our most advanced simulations consistently fail to replicate. A subtle radiance permeates the entire celestial expanse, originating equally from all directions. This ethereal glow has traversed nearly 13.8 billion years to reach us. Within its temperature fluctuations lies a detailed chronicle of the cosmos when it was merely 380,000 years old. This is the most ancient light detectable, serving for decades as our paramount instrument for comprehending the universe's genesis and early development. Its significance lies in its remarkable nature. In its infancy, the universe was incredibly hot. too hot for atoms to coalesce. It existed as a dense plasma, a pervasive fog of charged particles, and light inextricably entwined, preventing light from propagating freely. Subsequently, as the cosmos expanded and cooled, electrons merged with protons, forming neutral hydrogen atoms. This event effectively dispersed the fog, liberating the light. This pivotal moment is termed recombination, and the light emitted then is the cosmic microwave background. Its existence is well established, measured with extraordinary precision by numerous space probes. The minute temperature variations within this ancient radiance, mere fractions of 100,000th of a degree, encapsulate the nascent seeds of every galaxy, every cluster, and every filament that would eventually populate the universe. Our prevailing cosmological model precisely forecasts these temperature patterns. For years, the correspondence was exquisitely accurate. However, as researchers scrutinized the finer details more closely, a series of anomalies within the cosmic microwave background, previously dismissed as statistical noise, began to emerge. These include a significant region of markedly lower temperature than its surroundings, dubbed a cold spot, and an unexpected alignment of large-scale temperature patterns along a specific spatial orientation. A universe born from a random, uniform event should possess no inherent directional preference, no preferred axis, no special orientation. The fundamental laws of physics do not favor any particular direction. Yet the temperature patterns present in the universe's most ancient light exhibit a subtle alignment that defies theoretical expectations. This is currently classified as an anomaly, not a definitive discovery of novel physics. The ongoing debate regarding its authenticity, whether it represents a genuine phenomenon or a measurement artifact, has persisted for years. However, the James Webb Space Telescope Webb has injected a sense of urgency into these long-standing questions. If the cosmic microwave background harbors genuine anomalies, and if Webb is concurrently identifying galaxies that deviate from our models of cosmic structure formation, then it is plausible that these two issues are interconnected. It may be that the foundational elements for galaxy formation, imprinted within that ancient light, were not as random or as straightforward as we had initially presumed. Some theoretical physicists propose that the conditions prevailing just before or during recombination were more intricate than our current models account for. It is conceivable that exotic forms of energy were present, briefly influencing the expansion rate. Alternatively, the initial conditions of the universe might not have been perfectly uniform. The crucial question remains whether these anomalies are indicative of a genuine signal or merely random noise. What is unequivocally established is that Webb is rendering the noise considerably harder to dismiss. This is because one of the recurring patterns Webb is detecting in the distant universe directly correlates with those ancient temperature variations. When researchers overlay Webb's maps of galactic distribution onto the anomalies observed in the cosmic microwave background, the overlap is striking and, frankly, unsettling. It could be inconsequential, or it might represent the most significant coincidence in the history of cosmology. Regardless, the subsequent phase of this narrative delves deeper, profoundly deeper, into the very fabric of the universe's structure. When viewed from a sufficiently expansive perspective, the universe ceases to appear as a mere collection of individual galaxies. Instead, it takes on the appearance of a vast cosmic web. Intricate filaments of dark matter and gas stretch across hundreds of millions of light-years, interconnecting immense galactic clusters at their junctures. Vast, largely empty expanses, known as voids, where virtually nothing resides, are situated between these filaments. This overarching structure, the cosmic web, stands as one of the most visually arresting features of the universe at its grandest scales. Our theoretical models accurately predicted its existence. Supercomputer simulations, employing the physics of dark matter and gravity, generate outcomes remarkably similar to our observations. The cosmic web is largely situated where predicted, with an approximately correct distribution of filaments and voids. This has been considered a profound triumph of the standard cosmological model. However, Webb has begun to cast a shadow over this success. Across multiple deep-field observations, Webb has identified concentrations of galaxies in the early universe that are surprisingly advanced in their development. These are termed protoclusters, representing the nascent stages of what will eventually evolve into the colossal galaxy clusters observed today. The existence of protoclusters in the early universe is anticipated. The challenge, once again, lies in their temporal progression. Several protoclusters photographed by Webb appear to be further along in their maturation than our models suggest for their respective ages. They comprise a greater number of galaxies, exhibit more organized structures, and provide more evidence of gravitational cohesion than our most sophisticated simulations can account for at these early epochs. To grasp the magnitude of this, imagine observing a time-lapse of a city's growth, from a scattering of farms to a sprawling metropolis. A model might predict that after 10 years, you would observe small villages, after 50 years, small towns, and after a century, the nascent stages of a city. Webb, however, is examining the universe at 10 years of age and discovering that the metropolitan infrastructure is already substantially in place. One verified instance involves a structure observed at a redshift corresponding to approximately 1.5 billion years following the Big Bang. At this juncture, the universe is still exceptionally young. Yet, the structure identified by Webb contained dozens of massive galaxies already coalescing into a cluster, with filamentary connections discernible in the surrounding region. Theoretical explanations currently being explored encompass accelerated early dark matter clustering, modified initial conditions originating from the Big Bang, and the possibility that the initial generation of stars were both more massive and more numerous than our current models posit. Each of these colossal early stars would have experienced a brief, intense existence, culminating in a violent demise that would have enriched the surrounding gas with heavy elements far sooner than standard theory anticipates, potentially accelerating the entire process of galaxy formation. None of these proposed explanations have been definitively confirmed. All of them necessitate adjustments to our established cosmological framework. Moreover, the cosmic web itself might only represent the superficial manifestation of a more profound structure. Beneath the visible cosmic web, driving and shaping it, dictating the formation of filaments and the expansion of voids, lies a force for which no universally accepted explanation currently exists. This force has been designated as dark energy, and it constitutes approximately 68% of the total content of the universe. Webb is now beginning to probe whether our understanding of this enigmatic component is accurate, a question whose answer would profoundly alter our cosmological perspective. In 1998, two independent teams of astronomers made a discovery so unexpected that it garnered a Nobel Prize 12 years later. Their objective was to measure the rate at which the universe's expansion was decelerating. They assumed that gravity would act as a brake on the outward flight of galaxies and sought to quantify this effect. Instead, they encountered the opposite phenomenon. The universe's expansion is accelerating. Something is actively propelling space apart with increasing force. This invisible entity, uniformly distributed throughout all of space, possesses characteristics unlike any known particle or field. Scientists have christened it dark energy. Beyond this nomenclature, its fundamental nature remains unknown. Its existence is inferred from the observed accelerated expansion, but its essence is entirely enigmatic. Within the standard model, dark energy is characterized as the cosmological constant, representing a fixed energy density intrinsically woven into the fabric of space itself, uniform and unchanging across all of time and space. It is posited to have a single, constant value everywhere and always. This description has aligned with the observational data available for decades, but alignment does not not equate to explanation. The theoretical challenges associated with the cosmological constant are profound. When physicists attempt to calculate its theoretical value based on the principles of quantum mechanics, the resulting figure is approximately 120 orders of magnitude greater than the observed value. This is not a minor discrepancy. It represents the most substantial divergence between theoretical prediction and empirical observation in the annals of scientific history. Something is actively negating almost all of that predicted energy. Its identity remains unknown. This conundrum has been termed the vacuum catastrophe, and it stands as one of the most profound unsolved mysteries in physics. Webb is now contributing new data to this challenge by observing exceptionally distant supernovae with unprecedented accuracy. Webb is assisting researchers in determining whether dark energy is truly constant or if its properties have evolved throughout cosmic history. Early findings from Webb, corroborated by data from ground-based surveys, are yielding a tentative indication. It is merely a hint, not yet a confirmation, but it is noteworthy. The data appears to favor a scenario wherein dark energy is not perfectly constant, and its strength may have fluctuated subtly over cosmic epochs. If this is substantiated by future observations, it would imply that the cosmological constant is an inaccurate descriptor of dark energy. A variable dark energy would be referred to as quintessence, a field that, like other fields in physics, evolves over time. This is not a novel concept. Theorists have proposed it for years, but it has consistently lacked observational support. Webb may be providing the initial tangible evidence. If dark energy is not constant, then our model of the universe's future, our entire conception of its ultimate trajectory, requires revision. A dynamic dark energy could signify a different cosmic end than previously envisioned. And if dark energy is capable of change, then perhaps other aspects we assume to be immutable are, in fact, mutable. There exists a singular assumption underpinning all of modern cosmology that Webb's discoveries are subtly challenging. This assumption is so fundamental that questioning it borders on the philosophical. It pertains to the very rules governing the universe and their uniformity across all domains. Modern physics is predicated upon a principle so foundational that it is seldom explicitly stated: the cosmological principle. This principle asserts that, on sufficiently vast scales, the universe appears uniform in all directions and from every vantage point. It posits a universe devoid of special locations or preferred directions, a universe that is smooth and homogeneous when observed from a sufficiently distant perspective. This principle is not merely a philosophical construct. It is mathematically indispensable. Without it, the equations governing the universe's evolution become intractable. It is embedded within the very foundations of cosmology, and every model, simulation, and prediction relies upon it. Webb is now uncovering patterns that are instilling a sense of unease among some researchers regarding its validity. The most compelling challenge arises from a structure that was identified prior to Webb's launch: the Hercules Corona Borealis Great Wall. This immense aggregation of galaxies spans an astonishing 10 billion light-years in length. To contextualize this, the observable universe is approximately 93 billion light-years in diameter. A single structure of this magnitude should not exist if the universe is truly uniform at large scales. Our models impose a limit on the size of structures that gravity can assemble within the universe's age, a limit of roughly 1.2 billion light-years. The Hercules Corona Borealis Great Wall is nearly 10 times that size. Its existence has been a subject of considerable debate among researchers for years. Some contend that the detection methodology is flawed, while others argue for its authenticity, asserting it represents a genuine violation of the cosmological principle. While Webb is not directly observing this specific structure, it is contributing to the broader inquiry by identifying other large-scale aggregations that appear more pronounced than predicted by our models. Additionally, smaller-scale patterns are being flagged. In several of Webb's deep-field images, galaxies exhibit alignments that suggest they are responding to some large-scale feature or flow within the surrounding universe, a flow that our current models do not account for. If the cosmological principle is even marginally inaccurate, the ramifications would cascade across all of cosmology. The age of the universe, as determined from the microwave background, assumes uniformity. The expansion rate relies on this assumption, as do measurements of dark energy. Undermining this foundational principle necessitates a reassessment of substantial portions of the standard model. Most researchers exercise caution, acknowledging that perceived violations of uniformity might stem from observational biases. The inherent limitation of sampling only a finite region of space from our specific vantage point. What appears as a pattern from our perspective might not be so from another location. This represents a known constraint in cosmology. We possess a single universe and a solitary viewpoint, preventing us from stepping outside to verify our assumptions. What we can do, however, is intensify our scrutiny, and Webb is observing with an unprecedented level of detail. Every anomaly it uncovers, every galaxy found in an unexpected location, every structure that appears too vast, too ancient, or too organized, contributes another data point to an evolving panorama. This panorama is beginning to resemble less a series of minor adjustments to a robust model and more an indication of something far more profound. Furthermore, an additional layer lies beneath all of these considerations, a question that Webb has yet to definitively answer, but has rendered impossible to disregard. It pertains to the moments preceding the universe as we know it, and what, if anything, existed before the Big Bang. The Big Bang was not an explosion. This is a pervasive misconception in popular science. An explosion implies matter dispersing through pre-existing space. The Big Bang, conversely, was the genesis of space itself, concurrently with time, matter, and energy. In the conventional sense, there was no before, because time did not exist prior to that singularity. This has been the standard explanation, and, for decades, has sufficed. However, Webb is now prompting researchers to confront a question that the standard explanation struggles to accommodate. If the very early universe produced structures that our model of the Big Bang cannot explain, does the problem stem from events occurring after the Big Bang, or from the initial conditions of the Big Bang itself? A theory known as cosmic inflation proposes that, in the infinitesimal fraction of the first second following the Big Bang, the universe underwent a period of exponential expansion. Stretching from a size smaller than an atom to a scale larger than a galaxy in an almost incomprehensibly brief duration. Cosmic inflation was put forth in the 1980s to resolve several issues with the original Big Bang theory, including the observed uniformity of the universe and its seemingly flat geometry. Inflation is widely accepted, having made predictions that have been subsequently confirmed. Nevertheless, the precise details of inflation, its driving mechanism, its exact termination point, and whether it concluded uniformly across all regions, remain unknown. Some theorists posit that the anomalies detected by Webb, such as structures forming too early and masses appearing where they should not, point to non-standard initial conditions established during the inflationary epoch itself. It is conceivable that inflation did not generate perfectly random fluctuations, and that the seeds of cosmic structure were distributed in a manner different from our simplest models. Others venture further. A growing number of researchers are seriously investigating models wherein the universe observed by Webb did not originate with the Big Bang as we comprehend it. Instead, it may have emerged from a prior state, perhaps a cycle of contraction followed by a bounce, a continuously expanding and contracting universe, or a quantum tunneling event from a pre-existing substrate of space and time. These are not fringe notions. They are published in peer-reviewed journals by researchers at prominent institutions. While not confirmed, they're being considered with a seriousness that was absent a decade ago. the heightened consideration is precisely due to Webb's continuous discoveries. Every anomaly observed in the early universe represents a potential clue regarding initial conditions, and initial conditions are where the residual imprints of whatever preceded the universe, if anything did, would be concealed. The philosophical implication is staggering. If Webb's data ultimately compels a revision of our model of the Big Bang itself, it would signify that our most fundamental narrative of existence, the story of cosmic origins, is incomplete, not necessarily erroneous in every particular, but rather missing a crucial chapter at its very commencement. This missing chapter may prove irretrievable through observation, as the events of inflation and whatever preceded it may have erased their own evidence, dissipated by the very expansion that gave birth to the observable universe. However, Webb has unearthed an additional category of cosmic strangeness in the deep universe that connects the question of cosmic origins to something far more proximate. Something that reshapes our perception of our own place within this grand tapestry. This relates to the very first stars that ignited into existence. These stars were so peculiar, so colossal, and so dissimilar to anything extant today that they may have left an indelible mark on every galaxy ever photographed by Webb. For approximately 200 million years following the Big Bang, the universe was enveloped in darkness. This was not the darkness of an extinguished light bulb, but a profound, unprecedented cosmic void. There were no stars, no galaxies, no light generated by any celestial object, only hydrogen and helium gas, slowly cooling and settling into the gravitational cradles sculpted by the unseen dark matter, drifting in a silence that spanned the entirety of existence. Scientists refer to this epoch as the Cosmic Dark Ages. Then, approximately 200 million years after the Big Bang, the first stars flickered into existence. These are known as population 3 stars, and direct observation of one has never been achieved. They are believed to have been colossal, hundreds of times more massive than any star observed in the universe today, burning with intense blue light and consuming their fuel voraciously. Each of these stars would have existed for only a few million years before succumbing to a cataclysmic explosion known as a supernova. In their demise, they endowed the universe with something it had never previously possessed: heavy elements. Carbon, oxygen, iron, everything heavier than helium was forged within these primordial stellar furnaces and dispersed into the surrounding gas upon their explosive deaths. Every atom of carbon within your body can trace its lineage back to a star that perished before our own galaxy came into being. This fundamental understanding is confirmed in its broad outline. The specific characteristics of population 3 stars, including their precise masses, their numbers, and their distribution, remain unknown because no telescope prior to Webb possessed the capability to observe far enough back in time to detect them directly. Webb is attempting this very feat, and what it is discovering in the regions where these first stars are expected to have formed is generating new enigmas. In several observations, Webb has identified galaxies dating from the initial few hundred million years after the Big Bang that exhibit unexpectedly high concentrations of heavy elements. These are elements that, according to our models, should have required a considerably longer duration to form and disseminate through the stellar life cycle. The chemical enrichment occurred at a faster rate than our models predict. The most straightforward explanation posits that population 3 stars were even more massive and numerous than current estimates suggest, producing and distributing heavy elements with greater efficiency and velocity. A secondary, and perhaps more unsettling, possibility, given the totality of Webb's findings, is that the initial generation of stars included entities so massive that they collapsed directly into black holes rather than exploding as supernovae. These would be termed direct collapse black holes. They represent a theoretical pathway for the formation of the supermassive black holes observed at the centers of ancient galaxies, including the defunct galaxy described previously. If direct collapse black holes were prevalent in the very early universe, they could resolve two distinct puzzles simultaneously: the origin of early supermassive black holes and the rapid quenching of star formation in some early galaxies. This hypothesis remains theoretical. Webb has not yet confirmed the existence of direct collapse black holes, but it has captured images of objects in the early universe that are consistent with their presence. As the Webb telescope probes deeper into the cosmos, more intricate filaments emerge, each meticulously examined, leading to a shared, unsettling conclusion. Our established narrative of universal evolution is incomplete, missing a substantial fundamental piece. This missing element might be discernible within a specific measurement that has been a point of contention for scientific teams over several years. This measurement, now rendered with unprecedented precision by Webb, has only intensified the debate. Within astronomy, a particular cosmic structure possesses an inherent beauty. A spiral galaxy, characterized by two spiraling arms gracefully encircling a brilliant core, expanding outward like a celestial pinwheel suspended in the eons. Our own Milky Way galaxy exemplifies this form, as does the Andromeda galaxy, our closest significant galactic neighbor. Spiral galaxies are not elementary formations. Their genesis and enduring structure necessitate a precise set of cosmic conditions. The galactic arms are not solid entities, but rather constitute density waves, propagating through a disk of stars and gas, akin to ripples spreading across a liquid surface. The preservation of this form over billions of years demands a delicate gravitational equilibrium and a stable galactic disk, requiring immense spans of time. Consequently, astronomers were taken aback when Webb began transmitting images of the distant universe, revealing spiral formations in galaxies that, based on current timelines, should not have possessed such ordered structures yet. During the years 2022 and 2023, Webb captured imagery of numerous galaxies exhibiting distinct, organized spiral arms observed at redshifts corresponding to approximately 2 to 3 billion years following the Big Bang. At that juncture in cosmic history, prevailing cosmological models predict that galaxies should still be in a nascent, irregular state, coalescing through violent mergers, not yet having achieved the refined disk configurations essential for sustaining spiral arms. One such object, scrutinized in detail by a research group from the University of Manchester, displayed two clearly defined spiral arms with a resolution comparable to nearby galaxies imaged by considerably less powerful telescopes. The light from this galaxy had journeyed for over 11 billion years to reach Webb. At the moment that light embarked on its journey, the universe was merely 1/5 of its present age. The researchers themselves described their findings in a published report as unanticipated and difficult to reconcile with existing formation theories. To illustrate the complexity of this challenge, consider this analogy. Imagine observing a river's formation from snowmelt high in a mountain range. According to the prevailing model, it would take decades for the river to sculpt its channel, develop its sinuous curves, and establish a steady course. Yet someone presents a photograph taken merely 1 week after the snow began to melt, depicting a fully developed river. Wide, gracefully meandering, with established banks and a clearly defined waterway. This is precisely the scenario Webb has revealed. Stellar rivers already carved into elegant spirals at an epoch when the formative process should have barely commenced. The irrefutable fact is the observation itself. The spiral structures are demonstrably present and have been accurately measured. What remains elusive is the precise mechanism responsible for their early genesis. Contemporary simulations fail to replicate this outcome. Scientists are investigating the possibility that unusually smooth accretion of gas in the early universe might have facilitated disk formation more rapidly and quiescently. Others propose that the role of magnetic fields in early galactic evolution has been underestimated. Magnetic fields possess the capacity to stabilize galactic disks and mitigate the chaotic turbulence that impedes spiral formations. Neither hypothesis has been definitively confirmed, and both necessitate deviations from the standard cosmological paradigm. Webb's contribution to this ongoing inquiry extends beyond merely presenting new examples. It has introduced a statistical dimension. These spiral galaxies are not rare anomalies, but appear with sufficient frequency in deep field images to suggest that the process responsible for their formation was prevalent in the early cosmos. This prevalence challenges the notion that galaxies must endure a prolonged period of chaotic adolescence before attaining their mature forms. This perplexity regarding early galactic development connects to another phenomenon Webb has been investigating with increasing accuracy, occurring not across vast cosmic distances, but within the very nuclei of these ancient galaxies, something related to their growth. At the heart of almost every substantial galaxy resides a supermassive black hole. Our own Milky Way harbors one, possessing a mass equivalent to approximately 4 million suns condensed into a region smaller than our solar system. Nearby galaxies also contain these entities, some considerably more massive, with masses equivalent to billions of stellar masses concentrated into a single point of infinite density. The genesis of these objects remains one of astrophysics' most profound unsolved mysteries. Stellar mass black holes, those formed from the gravitational collapse of individual massive stars, are well understood. However, supermassive black holes, situated at galactic centers, represent an entirely different category. The transition from stellar mass black holes to objects billions of times more massive necessitates either an exceptionally prolonged period, an extraordinarily efficient process, or a combination of both. Current cosmological models permit the existence of supermassive black holes, but do not readily account for their presence as early in the universe's history, as Webb's observations indicate. Webb has detected what appears to be an active supermassive black hole at a redshift corresponding to roughly 400 million years after the Big Bang, an object that had already amassed a mass equivalent to several million stars. At 400 million years into cosmic history, insufficient time has elapsed for even the first generation of stars to complete their life cycles and expire. The crux of the issue is not the mere existence of the black hole, but the immense feeding rate required for it to attain such a colossal mass in so short a time frame. Black holes augment their mass by accreting surrounding matter. A fundamental physical constraint, known as the Eddington limit, dictates the maximum rate at which they can consume material, determined by the equilibrium between inward gravitational pull and outward radiation pressure emanating from the infalling matter. To form a supermassive black hole within 400 million years through conventional accretion would necessitate starting with an unusually large primordial seed and maintaining continuous accretion at the maximum possible rate. The probability of such an event occurring for a single black hole is exceedingly low. Webb, however, has consistently detected objects suggesting this phenomenon occurred repeatedly. To grasp the magnitude of this problem, envision attempting to fill a swimming pool using only a garden hose, but needing to accomplish this task in 30 seconds rather than 30 hours. The hose's flow rate is inherently limited. You would require either a substantially larger initial container or an entirely different method of filling. Scientists are exploring several potential avenues. The direct collapse black hole model posits that certain gas clouds in the early universe bypassed the star formation phase altogether, collapsing directly into black holes with masses of thousands of solar masses. A larger starting mass inherently reduces the subsequent growth required. Another proposition involves black hole mergers. If early black holes merged frequently and efficiently, their combined masses galaxies could accumulate more rapidly than individual accretion processes would allow. A third, still theoretical, possibility suggests that the Eddington limit could be exceeded under specific conditions referred to as super-Eddington accretion, which some simulations indicate is feasible within the dense environments of the early universe. What is unequivocally established is the presence of these objects. What remains undetermined is the specific pathway responsible for their formation. The significance of this inquiry extends beyond cosmology due to the intricate relationship between these early black holes and their host galaxies. Growing evidence suggests that supermassive black holes and their host galaxies evolve in tandem, exerting mutual influence in ways we are only beginning to comprehend. If these black holes predated the formation of their galaxies, it would necessitate a complete re-evaluation of galactic formation theories. A cohort of scientists has been observing this accumulating evidence with mounting concern. They do not dispute the data itself, but are troubled because their professional endeavors have been grounded in the very model that this new evidence appears to be dismantling. Scientific progress is often portrayed as a smooth, linear progression of discoveries, each building upon the last, progressively sharpening our understanding of reality. The actual process is far more convoluted. The current state of cosmology, beyond the fanfare of press releases and the awe-inspiring web images, is characterized by a professional and intellectual upheaval that is reshaping careers, prompting revisions of grant proposals, and compelling some of the world's most distinguished scientists to confront the possibility that the foundations of their life's work may be incomplete. It is an established fact that multiple prominent cosmologists have publicly acknowledged that the standard cosmological model is facing significant challenges. Surveys conducted within the astrophysics community since 2022 indicate that a substantial proportion of researchers express uncertainty regarding the lambda-cold dark matter model's resilience over the next decade without substantial modifications. For some, this uncertainty is a source of excitement, as the prospect of new physics is precisely what drew them to the field. For others, the pressure is genuinely taxing. Consider the implications for a researcher who has dedicated 30 years to developing simulations based on the standard model. Every published paper, every prediction made, and every student mentored would have been predicated on a specific set of assumptions. If these assumptions prove to be erroneous, their work does not vanish, but requires a fundamental recontextualization. And such a broad recontextualization, particularly late in a career, is a significant undertaking. Public disagreements have occurred at conferences, rarely making headlines, with debates centering on whether Webb's observed anomalies represent genuine phenomena or measurement artifacts. Arguments have arisen over statistical methodologies, and pointed exchanges have taken place in journal comment sections regarding the perceived overstatement of certain claims. Such discourse is inherently healthy, as disagreement serves as the mechanism by which scientific fields rigorously test themselves. However, beneath these disagreements, a broad consensus is coalescing around a single, uncomfortable conclusion. The data generated by Webb cannot be entirely attributed to measurement errors. Something tangible is being detected, and the central question is its true meaning. One researcher at a prominent European university, speaking at a conference in 2023, articulated the situation with remarkable candor. She likened cosmology's current predicament to that of a physician who has been administering a treatment that is effective in most cases, only to examine a scan suggesting the initial diagnosis was never entirely accurate. The treatment, she noted, still functions effectively most of the time. The majority of the universe continues to behave as predicted. Nearby galaxies, the cosmic microwave background radiation, and the large-scale cosmic structures mapped over decades largely conform to the prevailing model. The discord lies at the periphery, the very early universe, the vast cosmic scales, and specific measurements where increased precision has exposed subtle discrepancies. This challenge is not solely intellectual. It carries practical implications. Research funding typically follows established consensus. and grant proposals are evaluated within existing theoretical frameworks. Young researchers who pursue unconventional ideas risk professional marginalization before their careers are firmly established. Science is a human institution, progressing through argumentation and empirical evidence. At present, both are operating at their peak intensity. Amidst this scientific dialogue, a small cadre of theorists has been developing a framework intended to resolve many of Webb's observed anomalies in a single stroke. A framework that has been largely resisted by the broader scientific community for decades and necessitates a re-evaluation not only of galactic formation, but also of the very nature of gravity. In 1983, a physicist named Mordechai Milgram proposed a concept that the mainstream of astrophysics largely disregarded for many years. He posited that at extremely low accelerations, such as those experienced by stars at the outer peripheries of galaxies, gravity deviates from Newtonian principles, exhibiting a stronger effect than anticipated. He termed his theoretical construct modified Newtonian dynamics, though it is commonly referred to by its acronym MOND. The initial motivation for this proposal was straightforward: galactic rotation curves. The observation that stars at galactic edges orbit at speeds exceeding what would be expected based on the visible mass present had previously been explained by the existence of dark matter. Milgram proposed an alternative. Perhaps dark matter is an unnecessary construct, and instead, the law of gravity itself undergoes a change in behavior at low accelerations. For decades, this idea languished on the fringes of the scientific community. Dark matter possessed an overwhelming body of supporting evidence. With the cosmic microwave background, the universe's large-scale structure, and the formation of galaxy clusters all seemingly requiring dark matter in ways that modified gravity struggled to convincingly replicate. However, with the launch of Webb, certain patterns in its observations began to draw renewed attention to this long-standing question. Several of Webb's observations pertain to small, isolated galaxies in the very early universe that exhibit a greater degree of rotational structure and stability than standard dark matter models readily explain given their scale and age. In a limited number of instances, researchers working within modified gravity frameworks found that their predictions aligned more precisely with the observed rotation profiles than those derived from standard dark matter simulations. This is not definitive confirmation of modified gravity, but rather a reduction in the discrepancy between its predictions and observations in specific cases. At its core, modified gravity proposes the following. Imagine gravity as a flexible sheet. In conventional physics, this sheet possesses uniform elasticity throughout. In modified gravity frameworks, however, the sheet becomes subtly more elastic under conditions of very low tension. Stars exerting weak gravitational forces on each other across vast distances would experience a slightly stronger pull than predicted by Newtonian equations. The implications for galactic formation are considerable. If gravity is more potent at low accelerations, galaxies can maintain their structural integrity with less mass than dark matter models necessitate, allowing structure to form earlier and disks to stabilize more rapidly. Some of the early universe anomalies detected by Webb might naturally arise from a law of gravity that behaves differently than currently assumed. The primary challenge lies in ensuring this framework consistently applies across all cosmic scales simultaneously. Historically, modified gravity has demonstrated success at the scale of individual galaxies, but has encountered difficulties when applied to galaxy clusters and the cosmic web. Dark matter, despite its enigmatic nature, provides a better fit for these larger structures. Consequently, some theorists are now exploring hybrid models, suggesting that dark matter might exist but play a less dominant role than currently theorized, with modified gravity accounting for some of the structural influence presently attributed to it. These ideas remain minority viewpoints, yet the number of adherents has increased since Webb's deployment. What has been confirmed is that at least some of Webb's observations are more consistent with the predictions of modified gravity than with standard dark matter simulations. What remains unknown is whether this represents a genuine physical phenomenon or a coincidental alignment of specific observational circumstances. The resolution may lie in a fundamentally different type of observation, one that does not focus on galaxies themselves, but on the void between them, examining what is absent rather than what is present. For within the emptiest regions of the universe, something unexpected has been subtly accumulating in the observational data, potentially representing the most perplexing thread Webb has yet unraveled. Light operates within a defined budget. In the nascent universe, prior to the formation of stars, the pervasive hydrogen gas throughout space was in a neutral state. Neutral hydrogen is impervious to specific wavelengths of ultraviolet radiation. For the universe to transition into the transparent, star-filled expanse we observe today, a process had to occur that ionized all this hydrogen, stripping electrons from their atoms and clearing the cosmic haze. This transformative event is known as reionization, and it constitutes one of the most significant phase transitions in cosmic history. The Standard Model attributes the primary responsibility for reionization to the first stars. Their ultraviolet radiation, emanating intensely from newborn stars, gradually ionized the surrounding hydrogen over a period of several 100 million years. This broad outline is supported by evidence. Reionization undoubtedly occurred. The hydrogen was ionized, and the universe became transparent. What Webb's observations are challenging, however, is the energy budget involved. To fully reionize the universe, a specific minimum output of ultraviolet light from early galaxies is required. Scientists can calculate this threshold based on the physics of hydrogen ionization, a precise figure derived from well-understood atomic principles. When Webb measured the actual ultraviolet output of these early galaxies, it uncovered a surprising discrepancy. Many of them are producing significantly more ionizing radiation than theoretical models predicted. Some are generating 3 to 5 times the amount of ultraviolet light that galaxies of their size and age were estimated to produce. This finding does not invalidate the entire cosmological model, but indicates that our understanding of the processes within early galaxies, particularly the efficiency with which their young stars generate ionizing radiation, was substantially inaccurate. The importance of this finding extends beyond the reionization epoch itself. The efficiency with which stars produce ultraviolet radiation is contingent upon their chemical composition, their temperature, and the density of the gas from which they formed. If early galaxies are emitting more ionizing radiation than anticipated, it implies that the stars within them possess characteristics different from those modeled. Hotter, more massive, and formed from gas with distinct properties. Some researchers hypothesize a connection to the population 3-star problem discussed in earlier contexts. If the very first generation of stars was even more massive and energetic than previously estimated, their subsequent generations, born from gas enriched by their predecessors' demise, might have inherited some of this extreme efficiency. Others point to a property known as ionizing photon production efficiency, which appears to be systematically higher in early galaxies compared to those in the present-day universe. This suggests that star formation in low metallicity environments, regions with fewer heavy elements, inherently produces more energetic stellar populations. What is firmly established is the measurement. Early galaxies exhibit greater ultraviolet luminosity than models predicted, a finding consistently replicated across multiple independent Webb observations. What remains undetermined is whether this discrepancy reflects a systematic error in our modeling of early star formation, a fundamental difference in the physical conditions of the early universe, or an aspect of stellar physics that our current understanding has yet to encompass. Each of these anomalies, viewed in isolation, could potentially be attributed to calibration issues or gaps in our theoretical models. However, when considered collectively, they form a discernible pattern. This pattern points towards a unifying possibility that most researchers are not yet prepared to articulate explicitly, but which a growing number are documenting in their publications with careful, measured language. The possibility that the early universe operated under a set of physical laws that were not identical to those governing the universe today. This idea has a name and directly leads to the most profound question raised by Webb's observations. Physics is predicated on a set of fundamental numbers that are presumed to be invariant: the speed of light, the strength of gravity, the charge of an electron, and the mass ratio of a proton to an electron. These are designated as the fundamental constants of nature, and every equation describing the physical universe relies upon them. They are assumed to remain constant across all of time and all of space. What if this foundational assumption is incorrect? The hypothesis that fundamental constants might vary across cosmic time or space is not novel. Physicists have cautiously explored it for decades. The persistent challenge has always been observational. Detecting a change in a constant requires extraordinarily precise measurements spanning vast temporal or spatial scales, coupled with absolute certainty that genuine variation is being observed and not a systematic measurement error. Webb is now providing these highly precise measurements, and its findings are disquieting. One constant under intense scrutiny is the fine structure constant, which governs the strength of the electromagnetic force and dictates how atoms absorb and emit light by analyzing the spectra of extremely distant galaxies, specifically the wavelengths at which their gas absorbs light. Researchers can infer its value at the time that light was emitted. Multiple studies conducted over the years have yielded preliminary indications of such variation. Certain investigations of spectral data from remote quasars hinted that the fine structure constant might exhibit a minute variation, being somewhat diminished in one celestial direction and slightly elevated in another. This divergence was exceedingly small, falling well below 1%. Yet its directional nature was precisely the opposite of what one would anticipate from an immutable, universal constant. The James Webb Space Telescope, boasting superior spectroscopic accuracy, is now being employed to scrutinize these prior indications. The findings are still undergoing analysis and considerable discussion, with no confirmed observation of such a variation having been published to date. Nevertheless, should a variation exist at the magnitude suggested by earlier research, Webb's instruments possess the capability to detect it. The significance of this inquiry extends far beyond the realm of technical physics. If fundamental constants were not fixed throughout the cosmos, then the universe as it existed 1 billion years following the Big Bang would have been physically distinct. The governing principles would not have been identical. The intricacies of chemistry, the configuration of atoms, and the behavior of light would all have operated under subtly altered parameters. This could, in one sweeping explanation, account for why nascent galaxies appear incongruous with our current models, which are predicated on the assumption of fixed constants. If these constants were indeed variable, then every projection made concerning the early universe, utilizing those constants, would be systematically erroneous. The implications for humankind are profound. It would signify that the laws of physics, as we currently comprehend them, are not immutable, universal truths in the absolute sense. Instead, they represent the prevailing values of parameters that may have undergone evolution, akin to the diminishing temperature of a cooling object, or the decreasing pressure within a stabilizing system. This remains a theoretical construct. No definitive proof of varying constants has yet been established. However, the theoretical underpinnings are substantial, have undergone peer review, and are garnering increasing attention from mainstream physicists. Webb represents the inaugural instrument with sufficient power to rigorously test these hypotheses. Regardless of the ultimate outcome, the very fact that we are now probing whether the laws of physics have consistently been the laws of physics underscores the extent to which Webb has expanded the frontiers of scientific inquiry. These boundaries are poised for further expansion, as Webb has unveiled another discovery that links all these threads to a question that transcends mere scientific curiosity and touches upon the deeply personal. The majority of objects captured by Webb are extraordinarily distant. Galaxies situated billions of light-years away, light emanating from the very edge of the observable universe, entities that existed prior to our planet, our Sun, or even the raw materials that would eventually coalesce to form them. Yet, Webb has also directed its sophisticated instruments towards something considerably closer, environments conducive to planet formation. What it has discovered fundamentally alters the context of every other revelation in this narrative. In the year 2022, Webb captured imagery of the Orion Nebula with unparalleled detail. The Orion Nebula, a stellar nursery approximately 1,300 light-years from Earth, is a site where new stars are presently being forged from collapsing clouds of gas and dust. Within this nebula, Webb identified what researchers had posited but never clearly observed: potential rogue planets, objects with planetary mass drifting through space devoid of a parent star. These entities appear in pairs, orbiting one another in the open nebula without any gravitational tether to a star. Their presence suggests that the genesis of planets is not solely a consequence of star formation. Planets, or planet-sized objects, can form independently amidst the turbulent conditions of a stellar nursery. Webb has also commenced the direct analysis of the atmospheric composition of planets that orbit other stars. When a planet transits in front of its host star, a minuscule portion of the starlight permeates the planet's atmosphere. Distinct molecules absorb specific wavelengths of light. Webb possesses the capacity to detect these absorptions, thereby identifying the constituent elements of an atmosphere. In the year 2022, Webb confirmed the presence of carbon dioxide in the atmosphere of a planet designated WASP-39b, a gas giant orbiting a star approximately 700 light-years distant. This marked the inaugural clear detection of carbon dioxide within an exoplanet's atmosphere. Carbon dioxide is a molecule on Earth produced by both geological and biological processes. Its detection elsewhere does not inherently indicate the presence of life, but it unequivocally demonstrates Webb's ability to identify atmospheric chemical signatures with a precision unmatched by any prior instrument. More significantly, Webb has begun observing planets situated within the habitable zones of their respective stars. The habitable zone denotes the orbital range at which liquid water could exist on a planet's surface. Assuming adequate atmospheric pressure, several planets residing within habitable zones have now been observed by Webb. The analyses of their atmospheres are ongoing. No definitive biosignatures, which are chemical indicators of life, have been confirmed. However, the searches are active, and the quality of the data is such that if life exists within the systems currently under investigation, a detection would likely emerge within the subsequent several years. This brings us to the nexus of all the preceding points. Webb has unveiled a universe that formed in a manner divergent from our prior understanding, one that may operate under principles we have not fully grasped. And within this enigmatic cosmos, it is revealing that the conditions necessary for planet formation are widespread. It demonstrates that the fundamental building blocks of chemistry are ubiquitously distributed. We are not observing a universe inherently hostile to our existence. Rather, we are witnessing a universe more peculiar than we had envisioned, yet potentially more accommodating than we had assumed. What lies ahead is both sobering and remarkable, as Webb has illuminated the vastness of our ignorance, thereby reshaping the meaning of every answer we believed we possessed. Consider an inventory of the universe as currently understood: ordinary matter, comprising everything fashioned from atoms. All that is visible, all that can be measured by any instrument ever constructed, constitutes approximately 5% of the universe's total energy content. Dark matter, which is invisible and has not been directly detected, accounts for roughly 27%. Dark energy, an enigma in its nature and identified solely by its effects, makes up approximately 68%. This implies that 95% of all that exists is something we cannot perceive, cannot directly detect, and cannot explain from fundamental principles. We have assigned names to these components and developed mathematical descriptions of their effects, yet their true nature remains unknown. Prior to Webb, this inventory served as a humbling revelation. Now, with Webb's contributions, it carries an even greater urgency. Webb is revealing that the 5% we believed we understood, ordinary matter forming stars and galaxies under the influence of dark matter and dark energy, does not behave precisely as our models predict. The portion we thought we had deciphered is proving to be more intricate than anticipated. Ponder the mathematical implications if our model of 5% of the universe is flawed in ways that Webb is exposing, and if our descriptions of the remaining 95% are derived, in part, from that flawed model, then the inaccuracies are compounded. Minor errors in comprehending ordinary matter propagate into more significant misinterpretations of everything else. This is not mere conjecture. It is the logical consequence of how physical models are constructed. Each subsequent layer rests upon the one below. If a foundational element shifts, the structures above it will inevitably move as well. Several researchers have begun to articulate what they term the crisis of cosmological precision. The concept is that as instruments attain greater accuracy, they begin to reveal not only the outcomes predicted by our models, but also the specific points at which those predictions falter. Precision is not merely clarifying our view of the universe. It is more distinctly delineating the boundaries of our comprehension. A generation ago, cosmology celebrated what was termed the era of precision cosmology. Measurements had attained a level of accuracy sufficient to define the universe's fundamental parameters to within a few percent, including its age, expansion rate, and the density of matter and energy. This felt like the final touches on a complete depiction. Webb, however, is demonstrating that what appeared to be concluding details were, in fact, the prelude to a fundamental transformation of that picture. This phenomenon has occurred previously in the history of physics. In the late 1800s, numerous physicists believed that the fundamental laws were essentially finalized, with only a few minor discrepancies remaining. One such anomaly was the peculiar behavior of light, the resolution of which necessitated the revolutionary work of Einstein and a complete re-evaluation of our understanding of space, time, and gravity. The inconsistencies that Webb is now bringing to light are not minor. The Hubble tension alone involves two measurements of the same quantity that diverge by an amount that cannot be attributed to chance. The early galaxy mass problem spans an order of magnitude. These are issues of fundamental structure. History suggests that when significant structural questions accumulate within a mature scientific framework, the solution is not a mere amendment, but a new framework entirely. The precise form of this new framework remains unknown, but those who will construct it are already engaged in the work. Furthermore, several of them are focusing on a concept that most scientists have historically approached with caution: the possibility that the observable universe is not unique. When a scientific model encounters a breakdown, its replacement does not emerge fully formed. It evolves through a process of competition, where multiple frameworks are proposed, tested against empirical data, refined, and gradually one prevails. The history of physics is replete with such transitions. Currently, at least 4 serious theoretical frameworks are being developed to interpret Webb's findings. None of these have been definitively confirmed, yet all are actively researched by credentialed physicists who are publishing in prominent journals. The first approach is an adjustment to inflation, termed non-standard initial conditions. This framework retains most of the standard model, but posits that the inflationary period at the universe's inception did not proceed uniformly, instead perhaps due to a pre-existing structure or a more complex inflationary field. The initial seeds for galaxy formation were distributed in a manner that facilitated accelerated growth. This is considered the most conservative option, requiring the least deviation from established physics. The second framework involves early dark energy. This hypothesis suggests that a brief epoch of augmented dark energy existed during the initial few 100,000 years of the universe's existence before its dissipation. This surplus energy would have temporarily altered the expansion rate, leaving a residual effect that manifests today as the Hubble Tension. Several research groups have meticulously constructed models of early dark energy and are presently evaluating them against data from Webb. The third framework is interacting dark matter. The standard model assumes that dark matter interacts with ordinary matter solely through gravitational forces. However, this framework explores the possibility that dark matter particles also engage in weak interactions with each other or with photons in ways currently disregarded by existing models. Subtle self-interactions could influence the formation of dark matter halos, potentially enabling more rapid galaxy growth in the early universe and resolving the mass anomalies that Webb is observing. The fourth framework is the most radical. It proposes that the cosmological constant, which describes dark energy, is not constant at all, but rather that its properties have evolved over cosmic time. Recent data from extensive galaxy surveys, combined with Webb observations, have yielded an indication that dark energy may have been more potent in the past than it is at present. If confirmed, this would necessitate a complete overhaul of our model for both the universe's future and its past. None of these frameworks are currently complete, nor do any fully resolve all of Webb's observed anomalies. The field is characterized by a productive state of flux, precisely the condition that often precedes significant advancements. Imagine a jigsaw puzzle that is largely assembled, revealing a clear image. Then, someone introduces a new section of pieces, and these new pieces do not align with the existing image. They fit together amongst themselves, but not with what has already been placed. The puzzle assemblers are engaged in a debate. Does this new section belong to the same picture? Or does the original puzzle need to be dismantled and reassembled around these new pieces? Webb represents this new section, and the debate is ongoing. What all four competing frameworks share is a recognition that something within the standard model is either absent, incomplete, or demonstrably incorrect in specific ways that Webb has now made quantifiable. And the missing element, whatever it ultimately proves to be, will not only revolutionize astrophysics, but also fundamentally alter our perception of our own position within the grand narrative the universe is unfolding. This narrative possesses a human dimension that the data alone cannot fully capture, because the individuals engaged in this scientific endeavor are not merely executing calculations. They are grappling with the existential implications of inhabiting a universe that persistently defies complete understanding. There exists a photograph taken at the inaugural major conference where Webb's results were presented to the entirety of the astronomical community. In this image, a group of senior researchers is seated at a long table. Most of them have dedicated decades to their respective fields. Their faces are rapt with attention. One individual is observed with a faint smile. Another is looking down at notes with an expression that is difficult to interpret. They had just witnessed, presented sequentially, the anomalies that Webb had uncovered within its first year of operation. What the photograph fails to convey is the discourse that ensued in the hallways, dinner tables, and during late-night discussions, the very crucible where genuine scientific thought takes shape. Researchers who had been estranged for years reconnected through shared bewilderment. Long-standing disagreements were set aside in the face of novel data that neither faction had anticipated. Junior scientists, who had previously been hesitant to embrace unconventional ideas, discovered that their senior colleagues were suddenly more receptive to listening. This is the internal manifestation of a true scientific crisis, a quiet but significant readjustment. For physicists and astronomers who have dedicated their careers to the standard model, Webb's findings carry a distinct emotional weight. The standard model is more than just a professional framework. For many, it represents the very structure through which they have perceived reality for 30 or 40 years. It has informed their teaching, their writing, and their explanations of the universe to their families and students. One senior cosmologist, in a published interview in the year 2023, candidly described the experience. She stated that discovering anomalies of this magnitude, after decades of the model functioning so flawlessly, evoked less excitement and more a sense of vertigo, akin to standing on ground you trusted implicitly and feeling it shift beneath you. This feeling of vertigo is not a sign of weakness. It is the appropriate response to compelling evidence. The researchers experiencing it are also the most likely to achieve the next groundbreaking discovery, precisely because they possess a sufficiently deep understanding of the model to pinpoint exactly where it is faltering. For younger scientists, the situation presents different challenges. The career trajectories of graduate students and postdoctoral researchers are predicated on publications and grants derived from productive lines of inquiry. A paradigm shift introduces uncertainty regarding which avenues of research will prove fruitful. Several early career researchers have described in interviews the unusual experience of entering a field they expected to be nearing its conclusion, only to find it at the precipice of something entirely new. Some find this energizing, while others experience a sense of destabilization. Most feel a combination of both. What unites them all is the recognition that they are participating in a moment when cosmology is genuinely in a state of openness. Not merely open to minor parameter refinements, but open in the sense that fundamental questions, previously considered settled by the preceding generation, are being revisited. The universe that Webb is revealing is not diminished in beauty compared to the one described by the standard model. In many respects, it is more beautiful due to its surprising nature, its resistance to the comforting narrative we had constructed. Beauty in science does not necessitate simplicity, it demands honesty, and Webb is enforcing an honest appraisal of our knowledge and our ignorance. Perhaps no aspect of this story more starkly illustrates this honesty than the implications of Webb's discoveries for the possibility that we are not alone in this peculiar, expansive, rule-bending cosmos. The quest for extraterrestrial life is one of the most ancient inquiries in science, yet it is also one of the most nascent in terms of rigorous investigation. For the majority of human history, it resided in the realm of philosophy. Over the past 50 years, it has evolved into a data-driven discipline, and Webb has propelled this field forward in ways whose full impact will take years to comprehend. Prior to Webb, the search for biosignatures, chemical indicators of life within planetary atmospheres, was largely theoretical. We understood what to look for, but lacked an instrument capable of detecting it around any star other than our own. Webb has fundamentally altered this landscape. It can now analyze the atmospheric chemistry of planets orbiting other stars with sufficient precision to detect biologically relevant molecules. The list of molecules that could signal the presence of life includes oxygen, methane, carbon dioxide, water vapor, and a compound known as dimethyl sulfide, which on Earth is produced almost exclusively by marine microorganisms. While Webb cannot yet detect dimethyl sulfide with the required sensitivity for most targets, it can identify other molecules and is actively searching. Webb has detected water vapor and carbon dioxide in the atmosphere of a rocky planet within a nearby star system. This planet, designated K218b, orbits within the habitable zone of its star. Webb also detected a potential signal of dimethyl sulfide. Although researchers have prudently cautioned that this detection is tentative and requires further observation for confirmation, the detection of water and carbon dioxide in the atmosphere is considered confirmed. What remains uncertain is whether the observed chemistry reflects biological activity or purely geological processes. While caution is warranted, the detection itself is extraordinary. The broader context that Webb is constructing is also highly significant. By demonstrating that the early universe was capable of producing planets, and by confirming through atmospheric analysis that complex chemistry is feasible around a wide range of stars, Webb is establishing the physical framework for life as something the universe appears to widely accommodate. If Webb's anomalies in early galaxy formation are found to indicate a universe that constructs structure more rapidly and efficiently than we had assumed, that efficiency would also extend to planet formation. More galaxies forming earlier, more generations of stars cycling through their life processes and producing heavier elements, more rocky planets accumulating the chemistry necessary for complex molecules. A universe that generates more structure at an earlier stage also creates more potential abodes for life at an earlier stage. Consider the human significance of this observation. If life is prevalent throughout the universe, then the history of life on Earth is not an isolated anomaly in an indifferent cosmos, but rather one manifestation of a process that the universe has been running for billions of years across billions of locations. Conversely, if life is exceedingly rare, then the discoveries Webb is making about the inherent strangeness of cosmic structure become even more poignant. A universe, vast beyond imagination, governed by principles we are only beginning to comprehend, hosting perhaps only a single location where something looks back and wonders. Either possibility is astonishing. Webb will not definitively resolve this question, but it has undeniably shifted the inquiry from philosophical speculation to empirical measurement, from wondering to actively searching. And this search is yielding results that the subsequent chapter will directly address. This is because telescopes are currently under construction, specifically designed in response to Webb's findings, which will delve even deeper into both the question of cosmic structure and the question of life itself. The narrative is not concluding. It is merely commencing. Webb has demonstrated to the scientific community what is achievable. Now, that community is actively developing what comes next. Several major telescope projects are presently in development, each one conceived in part as a response to the specific questions raised by Webb. The first of these is the Extremely Large Telescope, currently under construction on a mountain in Chile's Atacama Desert, situated at an altitude of approximately 9,800 feet. Its primary mirror spans nearly 130 feet, exceeding the dimensions of any optical telescope constructed to date. Upon commencing operations, anticipated in the latter part of the 2027 decade, it will possess the capacity to directly capture images of rocky planets that orbit neighboring stars and meticulously analyze their atmospheres with a level of detail that the Webb telescope cannot achieve for the majority of its observational targets. Its resolving power is so exceptionally high that it could discern biosignatures within the atmospheres of nearby planets, operating at sensitivity levels many orders of magnitude beyond the capabilities of current instruments. The second significant undertaking is the Nancy Grace Roman Space Telescope, a mission spearheaded by the National Aeronautics and Space Administration, slated for launch in the middle of the 2027 decade. Roman will survey a field of view approximately 100 times broader than Webb's per individual image, enabling it to examine vast expanses of the sky for statistical investigations. This precisely addresses the enigmatic mass anomaly and the Hubble tension. While Webb delves deeply and narrowly, Roman operates broadly and swiftly. Collectively, they will furnish complementary datasets that neither instrument can produce in isolation. The third initiative directly confronts the Hubble tension. The Cosmic Microwave Background Stage 4 experiment is a terrestrial array engineered to chart the ancient light emanating from the early cosmos with an accuracy that surpasses all preceding measurements by a factor of roughly 10. Should the Hubble tension represent a genuine divergence in the fundamental physics of the early universe, this experiment is poised to definitively validate it and narrow down the spectrum of viable theoretical explanations. Each of these ambitious projects was conceived in response to specific lacunae in our understanding, initially identified by earlier telescopic endeavors and subsequently refined by Webb. They are not designed to confirm existing knowledge, but rather to rigorously test our hypotheses. Furthermore, a more speculative proposition is currently under deliberation within several space agency planning committees. This involves a substantial infrared telescope positioned in space, intended to peer even further back in time than Webb, targeting the very first stars and the transition from the cosmic dark ages to the emergence of the first light. If population 3 stars exist in detectable quantities, this telescope is expected to locate them, The ambitious scope of these projects mirrors the sense of urgency felt within the scientific community. Webb has not provided ultimate answers. Instead, it has clarified the profound questions, rendering them specific enough to guide the design of new instruments. This is what it signifies for the progression of our understanding. Assuming these projects proceed as planned and fulfill their technical objectives, the ensuing decade and a half of astronomical research will yield a greater volume of data concerning the fundamental architecture of the cosmos than all of the preceding century combined. This data will either substantiate one of the competing theoretical frameworks being developed to interpret Webb's observed anomalies, or introduce novel anomalies that none of the current frameworks anticipate. Both eventualities hold immense value, propelling our scientific narrative forward. And regardless of its ultimate direction, the story will invariably lead back to the same central question that has underscored all of Webb's discoveries. This is not merely a question about galaxies, expansion rates, or dark energy, but rather a fundamental inquiry into the very nature of the universe we inhabit and the implications of our existence within it. For the majority of recorded human history, the universe was conceived as the celestial dome, a canopy of moving lights above a flat terrestrial plane. Subsequently, our perception expanded to encompass the solar system, then our galaxy, and ultimately a colossal structure comprising billions of galaxies stretching across billions of light years. Each successive enlargement of our cosmic perspective necessitated the relinquishing of a more confined view. We are currently in the midst of another such expansion. The universe that Webb is unveiling is not simply larger, older, or more detailed than previous depictions. It is structurally distinct. Its formation followed a different trajectory, and it contains phenomena that were absent from our theoretical models. Its behavior defies our current explanatory frameworks, yet it remains the singular universe, the one that gave rise to Earth, the one that orchestrated the specific sequence of stellar demise and planetary chemistry that ultimately fostered life, the one in which, approximately 4.5 billion years ago, a terrestrial planet of moderate size settled into an orbit at an optimal distance from a stable, middle-aged star, developing oceans over the subsequent billion years, life over the following 3 billion years, and ultimately, creatures capable of contemplating the heavens over hundreds of millions of years. These beings are now operating a sophisticated telescope situated 1 million miles away, transmitting images of the universe as it existed within a few 100 million years of its inception. And the light it has captured reveals a universe that diverges from our most refined descriptions. This is not an indication of failure, but rather the hallmark of science functioning as intended. Every transformative revolution in the annals of physics has followed a discernible pattern: meticulous observations, the accumulation of anomalies, a period of theoretical upheaval, and finally, a groundbreaking insight that reconfigures our understanding and poses new, deeper questions. Isaac Newton elucidated gravity, thereby raising the question of its intrinsic nature. Albert Einstein provided an answer, which in turn prompted inquiries into the essence of space-time at quantum scales. The quantum revolution addressed some of these questions while introducing unresolved puzzles concerning measurement, locality, and reality. Each answer unlocks access to a more profound level of inquiry. Webb has opened such a door. What lies beyond it is presently a complex tapestry of competing theories, unresolved discrepancies, and empirical data that resists assimilation into any single, coherent framework. This position, while perhaps unsettling, is fundamentally honest. The truthful assessment of cosmology's current standing is this: we possess a model that accurately describes much of the universe under most circumstances, and a telescope that has pinpointed the specific instances where this model falters. Simultaneously, a dedicated community of scientists is intensely engaged in unraveling the reasons behind these discrepancies. The resolution will emerge, as it invariably does. It may necessitate the development of new physical principles, a revised understanding of dark matter or dark energy, or perhaps perhaps a fundamentally altered conception of the Big Bang and its origins. Irrespective of the ultimate answer, it will not diminish the vastness of the universe. Such outcomes are unprecedented. Every significant discovery in cosmology has, in fact, expanded our perception of the universe, rendering it more complex, enigmatic, and expansive than previously conceived. And within the next decade, a researcher poring over data from one of the next generation of telescopes will encounter a data point that deviates from the norm, a reading that contradicts the latest established understanding. At that moment, they will experience that unique blend of bewilderment and exhilaration that signals the genesis of every groundbreaking discovery. They will meticulously scrutinize the instrumentation, re-evaluate the calculations, and then commence the process of comprehending something entirely new. We initiated this exploration with a singular image, a minuscule patch of sky, no larger than a grain of sand, densely populated with thousands upon thousands of galaxies. Each one represents a cosmic metropolis containing hundreds of billions of stars, each with its own billions of years-long saga of formation, evolution, and eventual demise. This image is not a fabrication. The galaxies within it are real. The light that constitutes this image traversed a distance so immense that it defies human comprehension. Nevertheless, this image exists, and we created it. A species that has employed written language for approximately 5,000 years constructed a sophisticated instrument, positioned it 1,000,000 miles from our planet, and aimed it at a seemingly unremarkable point in the night sky, thereby receiving light that had been traveling since before our planet even formed. And the illumination it provided revealed a universe that does not perfectly align with our most advanced theoretical constructs. Galaxies appearing too ancient, structures emerging too substantial, black holes exhibiting masses incongruous with their age, an expansion rate yielding divergent values, ancient light displaying anomalous patterns, and a cosmos that seemingly coalesced with greater speed, efficiency, and intricacy than our established narrative suggests. What is the implication of residing in a universe that differs from our prior conception? Primarily, and most pragmatically, it signifies that scientific inquiry is functioning as intended. The fundamental purpose of developing instruments with enhanced precision is to identify the boundaries where our current understanding proves insufficient. Webb is performing precisely the task for which it was engineered. This is not a crisis, but rather a tool operating at its designed capacity. Secondly, it implies that the universe is not bound by our desire for simplicity. For decades, cosmological models converged toward an aesthetically pleasing and mathematically elegant framework. However, the universe has no obligation to remain confined within the parameters of our elegance. It exists as it is, and our responsibility is to comprehend its reality, not to impose our preferences upon it. Thirdly, this juncture represents a genuinely rare epoch in the trajectory of human knowledge. The instances when major scientific paradigms undergo fundamental shifts and new ones emerge are infrequent, occurring perhaps a handful of times per century within any given discipline. We appear to be experiencing such a transformative period in real time, observing its unfolding through the data provided by Webb. And fourthly, this signifies something more profound and less easily quantifiable. The universe is vaster than any model we have yet constructed. Each time we have believed ourselves to have grasped the entirety, it has been revealed to be merely a component. Each time we have presumed to have reached the ultimate depth, a greater complexity has been found beneath. This recurring pattern is not a cause for discouragement. It is the most consistent finding throughout the history of scientific endeavor. The universe has never, not once, proven to be smaller than we anticipated. It has never revealed itself to be simpler than we presumed. It has never confirmed that we had finally exhausted all avenues of inquiry. What Webb has gifted us is not a definitive answer, but rather a superior question. A question so precise that it compels the creation of new instruments. A question so urgent that it reshapes shapes career trajectories, and a question so profound that it can be contemplated in the quiet solitude of the night, gazing upon a sky that harbors more than we possess the capacity to measure. A telescope situated 1 million miles from Earth continues its vigil, constantly gathering light, ancient light, light from the very edge of our observable horizon. And within that light, the universe continues to communicate. We are still in the process of learning how to truly listen.